Now maybe yes. Done in collaboration with Mariana Gragna, Ruben Minasa, and Alessandro Tomasello, and also some work in progress with that Waldram too. The topic of the talk will be flux backgrounds in string theory, and we are all convinced that they are relevant for many aspects of string compactifications. For instance, from a phenomenological point of view, they provide mechanisms to stabilize moduli or to break supersymmetry, and also they are necessary on a more formal view of string theory to understand what is the phase space of the theory. Unfortunately, the knowledge we have of these backgrounds for the time being is based mainly on examples, and most of the examples are computed in the low energy supergravity approach. This approach is very useful in finding models that are perfectly consistent as far as four-dimensional theories are concerned, but it's not clear whether they are really embeddable in string theory. And in particular, one issue, which I will discuss later too, is compactness of these models. There are examples in 10 dimensions, and they are all related to Calabi-Yau's, either by dualities or they are simply conformal Calabi-Yau's. In this talk, I will first of all repeat once more our mantra that the generalized complex geometry is the right framework to describe flux vacua, and then I will show how we can use it to perform an exhaustive search for n equal 1 vacua, at least in a precise framework, which is six-dimensional nil manifolds and Soll manifolds. And also we'll try to show how we can use generalized complex geometry also to have some hints about non-geometric backgrounds. So we'll be looking for supersymmetric solutions of type 2 supergravity, where the space is a work product of Minkowski, four-dimensional Minkowski times a six-dimensional internal manifold. And for this background, it has been proven that actually we don't need to solve the equation of motions. It's enough to solve a set of first-order equations, which are the supersymmetry variations, and the equation of motion for the fluxes plus Bianchi identities. And exactly as without fluxes, supersymmetry tells us that the internal manifold must be Calabi-Yau. If we now impose supersymmetry with fluxes, the result is that the internal manifold must be a generalized Calabi-Yau. So there has been many hints at the fact that generalized complex geometry could be the right framework in which to describe flux backgrounds, and the idea is very, very simple. Basically, given a manifold, you work on a bundle which is the sum of the tangent and cotangent bundle. So the sections will be vectors plus one forms. And in a very rough way, we can see that the game is to extend differential geometry on this new bundle. So we can define a generalized almost complex structure. The integrability of this structure now will be given in terms of a new bracket, which is the current bracket. It's just an extension of the Lie bracket on T plus T star. We can define spinor on this bundle. The algebra now will be Clifford 6-6, since there is no identifications between upper and lower indices in the gamma matrices, and the spinors will be represented by sum of forms, and we will call a pure spinor a vacuum of the Clifford algebra. And if the manifold admits a closed pure spinor, the manifold will be a generalized Calabi-Yau. And this is exactly parallel to the standard Calabi-Yau condition for which everybody knows. The advantage of pure spinors is that pure spinors appear natural in supergravity, because if we take the tensor product of the internal components of the supersymmetry variation, you see that you can define a pair of polyforms, one a sum of even forms and the other one a sum of odd forms. And actually, basically by construction, those forms are pure spinors. They are also compatible in the sense that they have in common three annihilators, and hence they define an SU3 times SU3 structure on T plus T star. The explicit form of such pure spinors, of course, depends on the relation between the two spinors we have on our manifold. In the general case where the two spinors are neither parallel or orthogonal, it's given in terms of one vector which measures how not independent they are, and in a holomorphic two-form and a real two-form orthogonal to this vector. In the standard, the most familiar case of SU3 structure, you see that the two pure spinors are simply the exponential of the Keller form and the holomorphic three-form of the manifold. Once we have the pure spinors, we can actually manipulate supersymmetry variations and rewrite them as differential equations on these spinors. This is for type 2a and type 2b, and you see that they are mirror symmetric if we exchange the pure spinors and we exchange the Riemann-Roman fluxes. I want to stress that the content of this equation is exactly equivalent to the content of the supersymmetry variations. And moreover, these equations can also be obtained by considering calibrations of branes in these backgrounds. We again recover exactly the same set of equations. The point is that now we have the framework to give a general classification of a set of necessary conditions for an equal one flux backgrounds. We have first of all a topological condition, which is the existence of globally defined pure spin, two compatible globally defined pure spinors on the manifold. So the manifolds will all have SU3 times SU3 structure on T plus T star. And also we have an integrability condition, which tells us that those manifolds must admit a closed pure spinor, actually a twisted closed, because we have the twist by the three form, the Never-Schwarz three form. So all these manifolds must be twisted generalized Calabi-Yau. And the Ramon-Ramon flux is basically responsible for the non-integrability of the second pure spinor, so they play the role of a torsion for the manifold. So you can see that the classification is really parallel to what we have in absence of fluxes. There we will have a Calabi-Yau manifold. Here with the fluxes we will have a generalized Calabi-Yau manifold. One of the advantages of this formulation is that it is easy to prove that the equation of motion for the fluxes actually are not independent, but they are a consequence of supersymmetry. And to do that, it's enough to split into a real and imaginary part, let's say the non-integrable equation. And you can see that by simple manipulation, this lambda operator is simply the transposition of the forms, basically. By simple manipulations, you can see that star F, it's D plus H closed, so it's D plus H exact, and the equation of motions is automatically satisfied. This is important for our program because it means that once we know the metric and the B field, the Ramon-Ramon part is completely determined. We have the solution also for Ramon-Ramon. It is more complicated to prove it for the Never-Schwarz flux, but this was done recently in the case of Minkowski, while for Ramon-Ramon this proof also holds for ADS type of vacua. So we are left with Bianchi identity. Everybody knows that we have a no-go theorem in compactification telling us that if we want to compactify to Minkowski with fluxes on the internal manifold, we need to introduce negative charges or tension sources. And a way to see this for supersymmetric solutions is to look at the integrated Bianchi identity, because we can interpret this basically as a total charge that the flux contributes to the system. Here the charge is, the integral is over the full volume, and the imaginary part of phi 2 is the form that calibrates the cycle where the source is wrapped on. And again, using our form of the supersymmetry equation, it is easy to prove that the sign of this charge is always definite and is always negative, which means that we need orientable planes in order to balance this sign. This tells us nothing about, on the contrary, about the single contribution, so we can also have the branes in the system. Since we need orientable planes, we have to work out what is the action of the orientifold on the pure spinors. And this is it's nicely expressed in terms of again this lambda operator. And basically the idea is that the lambda, in this transposition, takes into account the worldsheet parity, which exchanges right and left movers. Once we have all the setup, let's say, to look for new vacua, the idea is to start seeing whether we can really find new vacua which are not related to Calabi-Yaus in any way, in a sort of a controlled environment. And this controlled environment is provided by nil manifolds and solved manifolds, which are, in a sense, simple geometries, but the good thing is that we know a lot about their properties. So these manifolds are parallelizable manifolds. They admit a set of globally defined one-forms or vectors. They are homogeneous spaces, and they can be interpreted as a quotient of either a nilpotent or solvable group by a discrete subgroup. And the action of the discrete subgroup is responsible for the twisted identifications on the manifold. They are also called the twisted tori because they can be interpreted as iterated torus vibrations. One very well-known example is the nil manifold associated to the three-dimensional Heisenberg algebra, and there you can see that the twisted identification of the x3 coordinate is needed in order to have a well-defined one-form E3. What is now, the reason why, one of the reasons why they suited our exhaustive search program is that we have a complete classification of those manifolds in 6 dimensions, and there are finitely many. So this is already a good starting point. There are 34 nilpotent algebras, hence nilpotent manifolds, and 182 solved manifolds. An even more important issue for us was compactness. In order to make a group manifold compact, we can quotient it with a discrete maximal subgroup. The point is to see when such a discrete group exists. And for nil manifold, it has been proven that actually it is a necessary and sufficient condition the fact that the structure constant must be integer in a certain basis, which is the Maltese basis, and they have to satisfy the unimodularity condition. So the sum of the upper and lower indices must be 0. For solved manifold, it is less easy because those two conditions are only necessary. But luckily enough, there are sufficiency criteria, and we picked up one given by Saito, which applies only to algebraic groups. And going through the list of all the solvable algebras, we found 13 truly, let's say, compact solvable groups, plus, of course, the 34 nilpotent, which are a special case of solvable algebras. The curvature of those manifolds can be computed easily from the structure constant. And for the nil manifold, we can see that they're all of negative curvature, while for solved manifold, they can be either negative or 0 curvature. Another interesting thing for us is that it was proven recently by Cavalcanti and Gualtieri that all nil manifolds are generalized Calabi-Yau. So in a sense, the first part of our program was already done by someone else. So as I just told you, without Ramon and the short fluxes, nil manifold at least are generalized Calabi-Yau. And we know also that by themselves they are not solutions of supergravity because the curvature, they have negative curvature. So the idea is to turn on fluxes, see whether they can compensate in a sense the negative curvature and whether we can produce supersymmetric solutions of supergravity. Here I say at least n equal 1 solutions because the way the procedure we use in order to compute such solutions is to pick up a pair of compatible pure spinors. But since these are trivial, the structure group is trivial on this manifold, they are parallelizable. Actually, we have many pairs of pure spinors, so it is highly possible, you can check, that actually, given a certain model, there are extra supersymmetries on top of the n equal 1 we picked up. And also, actually, we limit a little bit our search because we don't pick up the most general pair of pure spinors I've just shown you, but we decide to work with a definite structure. So either pure spinors associated with an SU3 structure on the manifold or a fixed static SU2. And the procedure to compute solutions is first to look for what we call global solutions. So we go to the large volume limit of our solutions. The work factor is constant, is 1, and the dilaton as well is equal to the same coupling. And the advantage of this solution is that now all the objects we have on the manifold are basically constant when expressed in the basis of the left invariant forms that define the algebra associated to the manifold. So we have a high simplifications of the equations because basically they are algebraic. This procedure is absolutely correct, let's say, for nil manifolds, since another property of nil manifolds is that the rank cohomology is isomorphic to the left invariant cohomology. It is less kosher, let's say, for solved manifold, where this isomorphism doesn't hold, and then we may be missing solutions. Once we find a global solution, the idea is then to promote it to a local one by reintroducing the work factor. And the way there could be other ways. The way we try to reintroduce the work factor is to rescale all the one forms we have on the manifold by the warping. And since a priori we can have intersecting sources, we have different work factors. We choose a dependence of these work factors only on the transverse directions to all the sources we have. And the scaling is done with a plus or minus sign depending on whether the one form is along the source or transverse to the source. So in spite of the huge number of manifolds we have, we actually found very, very few vacua. We found some Minkowski, all the possible Minkowski vacua satisfying the hypothesis we made, and they are of two types. There is one class which is very well behaved in a sense. And they are dual, T-dual, to conformal Calabi-Yau with fluxes. So there's nothing new there. They're just a warped version of the solutions that Cacru et al. Found some years ago. And the main feature that makes those models easy, easily extendable to local solutions, is the fact that they only have one type of source. Then we find the truly new solutions, which we call multi-source solutions. They correspond to the localized source, in the sense that when we go to, as I said before, we take the large volume limit. Basically, our Bianchi identity now is not really the local Bianchi identity, but we assume to smear all our sources in the transverse directions. So that's why they're, in fact, the localized sources. They're not liftable to a local solutions, and the problem in reintroducing the warp factor is the fact that we have intersecting sources. So we're back to a known problem, how to find intersecting brane or in general sources solutions. And then we found also a few vacuas which are ADS, so in type 2A theory. In this case, we have to introduce in our equations the cosmological constant. So we will not have anymore the generalized Calabi-Yau conditions, but they will become generalized half-flat manifolds, because the conditions supersymmetry imposes are a straightforward generalization of the half-flat conditions that people found for SU3 structure manifolds. Just to give an example, I show you the only solutions, let's say, new solution we found for the Neel manifolds. This is the algebra associated to the Neel manifold, and we put an orientifold in the 4-5 directions. This is the structure of the Neel manifold, where you see the iterated fibrations, torus fibrations I mentioned before. And for this vibration structure, you can also see that why this is not T-dualizable back to an O3 solution, because in order to get the O3, we should do T-duality in 4 and 5, but 4 and 5 are not isometries of our manifold. The solution is for SU3 structure, so this is, is the form of the pure spinors. We only have a non-zero Ramon free-form flux. And if you look at the Bianchi identity for this flux, you see that actually our O5 plane we just put at the beginning is not enough. And we have to introduce another orientifold, this time in the direction 2 and 6. This orientifold is compatible with the previous one, so this is actually a solution. Once we impose this extra projection on the moduli, we are left with 3 Kähler moduli and 1 complex structure modulus. There are some extra constraints on these moduli. For instance, the positivity of the metric imposes that all the Kähler moduli must be positive. And if we look at the integrated Bianchi identity, so at the global charges of our fluxes, we see that actually the Kähler moduli are not independent. They all depend on the complex structure one. And if the other interesting thing, the first question you can ask is, okay, you're in a large volume, but are you consistent with this approximation? Yes, because if you compute the volume of the 2 cycles on which we can wrap our sources, and these are T1, T2 times TR and T3, V is the overall volume of the manifold, you can see that we can tune the string coupling and the volume of the manifold in order to have weak string coupling and large volume, and all the cycles with a large volume. Again, we couldn't lift it to a full solution because we have intersecting sources and we don't know how to deal with the warp factor. So up to now I only described geometric solutions, so our backgrounds are real manifolds. But actually it seems that string theory contains a much wider class of solutions. And these solutions appear naturally if we stay in the 4-dimensional effective approach. And they appear from different sides. For instance, Shelton, Taylor, and Beck, they prove that if you want to impose, if you want to have superpotentials into A and to B, which are invariant under T-duality, you need to introduce extra, let's call fluxes, on top of what we already have, the torsion, the F, the torsion, and the Navier-Schwarz flux. And these fluxes can be interpreted as a subsequent T-dualities, each separate flux, as subsequent T-dualities on the Navier-Schwarz field. They are non-geometric because you see that you need to perform T-dualities on more than one leg on the H flux. These non-geometric fluxes also appear in the formulas of SU3 times SU3 effective actions, because those actions that contain much more gauging than the ones that torsion and fluxes can provide. And in particular, it has been shown that those gaugings, this non-geometric gauging, are necessary if you want to compute the mirror of Calabi-Yau with a magnetic Neveu-Schwarz flux. And again, another way to see how these non-geometric fluxes enter in supergravity is to look at the standard four-dimensional supergravity actions. Typically, these are gauge supergravities. And if you look at the algebra for the vectors, you have an abelian part, also for the vectors that come from the reduction of the B field gauge transformations. And you know that in geometric compactifications, you can't have non-abelian algebras for those vectors. So for the four-dimensional point of view, it seems that geometric and non-geometric backgrounds are really on the same ground. They appear in effective actions. The problem is that it's not clear how to interpret those backgrounds in 10 dimensions. And this is what we would like to do, but this is still a work in progress. And for the time being, what I will just show you is that we can give, at least for the Q fluxes, the R fluxes are, we don't know how to deal with them. At least for the Q fluxes, we can give an interpretation in terms of 10 dimensions. In particular, we can see that the algebra of the gauge vectors, here V are the isometries and X's are the B field gauge transformations. This algebra is equivalent to the Courant bracket. This is a Lie bracket. So the Courant bracket computed on the section of a bundle associated to the manifold, which is a generalized tangent bundle. And for parallelizable manifold, we can also propose an interpretation of what non-geometricity in T-duality is, because T-duality appears just as a symmetry rotation of the fibers of this generalized tangent bundle, and the geometricity or non-geometricity comes when we try to go back to the standard T plus T star. So it's a global issue about the gluing conditions that we need in order to have well-defined sections on T plus T star. To see this, we can use the beloved example of the 3 torus with K units of Neveu-Schwarz flux. We can choose a gauge where the B field is in the 2 and 3 direction. And we can define the generalized tangent bundles of this manifold. The generalized tangent bundle has fibers which are T plus T star. The difference is that now, so the sections are again the sum of a vector and a form, but now the forms are not well defined in the sense that they do not patch with diffeomorphisms, but we need a gauge transformation, which is a transformation of the B field, in order to patch them on the overlaps. And again, we can try to see what is the relation between this generalized tangent bundle and T plus T star. We can define a sort of I don't know how to call it, projection isomorphism, as you like. And basically, the idea is that we have to shift our form on E in such a way that once reduced to T plus T star, transform as a good section of T star. The vectors do not pose any problem; they're good sections in any case. So we assume that we can define a basis for the sections of E. This basis is very simple. It's simply a combination of the vectors in one form that you have on T plus T star of the torus. And the choice of the basis, if you look at the identification between T plus T star and E, is simply such that when we go to T plus T star, we have the standard basis of vectors N, so the del I and the xi. If we now compute the Courant bracket on this basis, we see that we get this algebra, which is a piece of the geometric part of the gauge, of the four-dimensional gauge algebra I showed you before. In this picture, the fibers of the generalized tangent bundle, they have an O3, in this case, an O3-3 symmetry. They have an O3-3 structure group, and we can interpret T-duality simply as a subgroup of this symmetry. So T-duality is simply a rotation on the basis of the E's. And here we will, since we can interpret the torus as a T2 fibration over a circle, we can perform, for instance, T-duality in a X3 direction. Roughly speaking, this exchanges vectors and forms in the third direction, and we get this new algebra basis for the sections of E. And if we now compute the Courant brackets, you recognize the Heisenberg algebra I showed you before. If we now want to go back to T plus T star, we need to see what is our isomorphism, and we have to choose. And actually, this is very simple, because if you look at the transformation under a shifting X of our vectors and forms, you see that they are independently well defined. So here we really have already on E sections of T plus T star. So the isomorphism requires a 0B, and we end up with in a sense, we have a good section of T plus T star, so in a sense we have a good geometry. If we look at the same model in the standard way, so we start with our torus with H flux and we perform a T-duality a la Busher, this is what you get. We know this is a twisted torus I showed you before. So the H flux has become the torsion, the twist, the torsion on the manifold which is responsible for the twist. And again, also from that point of view, we see that we still have a good geometric description because in order to patch our vectors, forms, or whatever, the metric and the B field, we need simply an element of SL to Z, so a geometric transformation. We can go further and perform another T-duality in the direction X2, and so we get a new set of bases. We can compute again the Courant bracket, and this is the way non-geometricity appears here. So you see that now the algebra includes the non-geometric fluxes I showed you before. And a way to see why we are non-geometric here is again to try to go back to T plus T star. And here you can see that under the shift in X1, now the forms are well defined, but the vectors are not. So we couldn't find, it's not possible to find any B, so any gauge transformation of B such that we can patch the vectors in a good way in order to have sections on T. We could do it a priori, introducing a new type of isomorphism, which is using not a two-form, but a bivector. And actually, this is compatible. This is what also Busher rules will suggest, because we know that if you have a two-form, we do two T-dualities in the directions of the form, of the legs of the form, we get a bivector. But the problem is that now, so locally, there is no problem. Locally, a priori, we can define a map between E and T plus T star. So locally, T-duality in a sense holds. We have a geometric description locally, but the problem is global, because if we now try to glue our bivector on the different patches, there is no gluing procedure, there are no cocycles you can define, so there is no global notion of T plus T star. In a sense, we don't have a manifold anymore. And again, if we look at this in a standard way, we continue with our Busher rules, now we end up with this metric and this B field, and you see that they're not independently well defined under the periodicity in X1. So again, in order to patch them, we need an 1-to-2 transformation. So this is an example of T-fold, and again, this is a manifold which has a local geometric description, but not a global one. But from the point of view of E, T-duality is very simple. It's just a change of basis on the fibers. So basically that's the end of the story. So I hope I convinced you that generalized complex geometry is a good framework in which to study flux vacua. At least it provides a very general, maybe empty, but very general characterization of those manifolds. It can help in interpreting also non-geometric backgrounds from the string theory point of view, not in 4 dimensions, and at least allowed for finding at least new, maybe few, but new vacua, which are truly generalized Calabi-Yau, they're not conformal Calabi-Yaus. We found those, unfortunately, are very few. One in manifold, the one I showed you, and 4 manifolds on the same solved manifold. They all correspond, this new vacua, to intersecting sources, so they're global solutions, they're not local ones, and they all have some moduli unfixed. Of course, this is not the end of the story. You could go on and look for different spaces. For instance, you can look for non-algebraic groups. You can also try what we did when we were looking for compact manifold was to only take the quotient by a discrete group, but actually you can make a 6-dimensional compact manifold by quotienting a higher dimensional algebra by a continuous group, and this we didn't consider, so this could be another place where to look for new vacua, and of course you can also try to look for non-geometries. And that's all.
Any questions?
Are the O-planes the sources for the negative scalar curvature on the nil manifold?
Yeah.
Do you have to take them to be smeared out?
We have to take the smearing because we are in the large volume limit.
Okay. Thanks.
Can you take, so there's some, can you take the cover of the orientifold action around the O-planes and get some kind of smooth manifold? And if so, are there some equations that characterize that smooth manifold?
This we have a look at. To be fair, I have no answer for that. But it's, for instance, what we have to do now is to see how to interpret what are the orientifolds on this generalized tangent bundle. This is something we still have to look at.
So you had this discussion on the algebra of currents, right? So presumably, since the action is non-geometric and so on, you would have to phrase this whole thing in terms of a conformal field theory.
Well,
so can you find a conformal field theory that has this algebra, or could it have this algebra?
there are examples. For instance, in certain cases, and this is the T-fold of Hals, they prove that they correspond to a consistent conformal field theory.
Yeah, what I really meant is one in which you had various structure constants.
No, with the Qs.
Oh, okay, but only the Qs. But can you have some that has both the Fs and the Qs and the Hs?
I think so, but I'm not sure about that yet. What you can't, what you don't have as a description of a conformal field theory is with the Rs.
Yes. What can you say in general about the modular space of these manifolds? Because about the modular space, because you can use the standard complex structure and Keller complex modulus in Clavellado, I guess.
Well, this is what Mariana, Jan, and Dan has done. Basically, what you can do is to use the generalized complex structures which are associated to these manifolds and which are generalization of the standard Keller and complex structure moduli. And then you perform a reduction in such a way that the effective action has still the properties of n equal to 2 actions that you would get from Calabi-Yau. So in the effective low energy theory, you still have the notion of a...
So I guess we need to think. One more question.
One quick question. Have you studied the M theory lift of the type 2A side?
There is a discussion of the M theory version of that done by Hull in his last paper, but there the extension you need is different from the extension with the gerb we use here.
Okay, let's thank Michela again.